Hello everyone, in this video we will discuss the step 9, how can we tune the gain, integral, and derivative parameters of the PID controller. Rather than rely on some tuning method or setting rules, for example the Ziegler-Nichols method we talked about from the previous video, in this video I will tune the PID parameters through the system response and my personal experience. This will be the same idea as the most of the cases. I will tune the PID parameters based on the system response. Okay, let's go to the TrinkCAD 3. Before you tune the PID parameters, we better set the PID controller into manual mode and make sure the system is working under a stable status. When we tune the PID parameters, we better make the system working around its operating point. For example, if your system that working operation point that is 100 centigrade, so you better making the process working around 100 centigrade. Take my system as an example. My system that operating point that is 40 centigrade, so I will tune the PID parameters and toggle the PID output in manual mode or auto mode. Basically, make my process value working around 40 centigrade. And in my system, when the system works around 40 centigrade, my output, that operating point that is 25%, and the temperature that is 40 centigrade. So currently my PID controller that is working under the manual mode, and my PID output working under the manual control I set 30%, and the process temperature that is the 37.9. When you tune the PID parameters, you need to set up the online trend. You can clearly see the behavior of the process, and based on the system behavior, we can increase or decrease the PID 3 parameters. The basic sequence to tune the PID 3 parameters, we will start from the gain, and then do the integral, and the left, that is a derivative. Firstly, we will start from the gain. But if you set gain is a very low parameter, maybe your controller or maybe your actuator cannot totally control your process. If you set too high on the gain, your actuator will be too sensitive to the noise. So that means the value of the gain should not be too high or too low, should be a certain value. We will, based on our experience, use one value as the initial value of the gain, and then increase its gain to see the behavior of the process. So how can we select one value as the initial value of the gain value? From my personal experience, we can give a system a couple times stable response. Basically, we will know what the gain on our controlled object. Basically, our PID gain will be the 1 over the process gain, and maybe times 2 or 3 times of this 1 over gain. Okay, let me show how can we do that. So firstly, let's turn on our online train. And currently my PID working under the manual mode, and my process that is a cooling system. So to make this process have a step response, I can decrease my output from 30 to 20. The temperature process will have a rising step response. So let's set a 10% difference on the output. So I will change from 30 to 20 and hit this button, right value. And then you will see the right curve, that is the output control, and the dark blue, that is the process value. And meantime, we can turn on this noise. I introduced this from the previous video. I'm using 1 second order process model as my controlled object. In time, I can enlarge this window so that we can see the whole process of my process change. I will make a small note here. Output change from 30% to 20%. And the process value will start from the 38 centigrade. We start from the 38 centigrade. And now likely the system reach its stable status. And now the temperature that is 42 centigrade. So let's do a rough calculation first. So that means the gain of our process. We need to use the delta change on the process value over the control delta change. So this temperature change, it changed 4 centigrade. 4 over the output change, that is the 10%. I will over 10. So that means my process gain, that is 0.4. Okay. And our PID initial gain setting could be 1 over this GP. And after this, we can use this 1 over this process gain and times 2 or times 3. If your system has a strong noise, like my system here, it has a noise. Personally, I will prefer to use a 2. But if your system, the noise is not too strong, so you can start from the 3. So follow this way, 1 over 0.4 and times 2. That is a 5. Meantime, we will set the integral value to a very big value, for example, 200 seconds, and set the derivative value to a 0 value. Basically, get rid of the integral and derivative effects in the PID control. So that means we purely start from the gain only. So we will prepare the PID parameters monitor into this watch table. Okay, so let's jump to the control PID program, and all our PID controller parameters under this structure. So I will leave the mouse around here, right click, click this add watch. This whole parameter structure will be added into this watch list. So from here, we can set this gain, integral, and the derivative value. Okay. If we record this Beckhoff PID controller, the gain, that is the KP, Tn, that is the integral, and the TV, that is the derivative value. TD, personally, I will prefer to set 0.5. This KP, Tn, TV, that is our main parameters we need to tune. Okay, so we will set this gain at 5. And set this integral value to a very big value, for example, T upon 200 seconds. Okay, very huge value. Basically, get rid of this integral. And TV, we will set 0. Okay, and click this write the value. And now we prepare this gain only, and get rid of this integral and derivative effects. And then let's shift to the controller into the automatic mode. And before we set the automatic, we also need to prepare this set point. And for example, now the process value, that is 42. We can prepare this set point into 30. So to set this set point, I will set this value 30. Okay, and after we set 30, this is a new set point. Let's shift to the controller PID into the automatic mode. To change this mode, we can double click here and switch to this PID into automatic mode. Mode active, enter, and click right. So now the PID is working under the automatic mode, and our set point, that is 30. The PID run the gain only. So let's go to the trend. System working under the automatic mode, and this is the new set point. And the PID is working under the P, this gain only. I'm speeding up this video, this transition process in 5 times, so we can have a overall picture on this process change. So from here we will see, because our PID is working under the gain only, so this process value always has an error, has this residual with a set point. If we increase the gain, this residual between the set point and the process value will be decreased. However, this error will be always here, because this gain relies on this error to control this PID output. That is the gain only. It always has this error. If we increase this gain, we will see this error will be decreased, but it always present here. If we increase to 10, for example. That is a very huge gain for this system. We will see the error between the set point and the process value, it is decreased, but this error is still there. If I decrease this gain, for example, if I change to 2, we will see this error will be increased. The error between the set point and the process value, it is increased. When we set the gain on 5, that error is here. This is the gain on 10. This is the gain on 2. So likely, if we set the gain at 6, roughly this gain can be used as an initial value. So let's set the gain to 6. Even if we increase the gain, it will decrease this error. However, the higher gain that will cause the actuator very sensitive for the error, for the noise. So we better set the gain in a certain value, not too high but not too low. That's why I set 6 as the initial value. And to get rid of this error, we can involve the integral, because the integral can get rid of this error here. And keep in mind, the integral, this Tn is at a denominator. That means the smaller of this Tn value, the stronger the integral in fact will do. So to increase this integral in fact, so we need to decrease this Tn. So currently this Tn value, that is 200. So we can decrease this Tn value to maybe 20 or 30. For example, I will set T upon 30 seconds. And we can watch this process feedback. To see the performance of the integral, we need to wait for a while, because integral need a certain time to accumulate the value inside. So we need for a while. For this system, basically we would need 1 minute or 2 minutes to see the final results. And from this feedback, we will see, even if the system has a noise, but we will still see this process value almost reach to 30. It's walking around 30. That means basically this error between the set point and the process value is basically eliminated. And after this, we can steadily change the set point. The set point could walk around our operating point. And again, my operating point, that is a 40 centigrade. So we can set my set point to 45. And let's see the performance of the control and the process feedback. So the green line, that is a new set point. And our current gain, that is a 6. And the current Tn, that is a 30 seconds. The process value approach to this set point, but this speed is really slow. That means we can make this integral a little bit stronger, make this process value reach to this set point a little bit quicker than before. So to implement this performance, we can decrease this Tn. We can decrease this Tn to 25 for a try. Let's set 30 again. Make sure this is the same as here. We can compare them. So we can see with a 30, this integral, this error is limited very slow. So that's why I decrease this Tn to increase this integral in fact. Okay, so this decrease process shows a very good performance now. Likely, this Tn, this 25 works for this system. And when the system reaches a stable status, let's set 45 again, and let's compare these two times. Alright, so the system basically is stable, and let's set 45 again. This time, this error between the set point and the process value comparing with the first time, so actually this process approached this set point quicker than before. And in the meantime, we can also increase this KP a little bit, because the higher of the gain, the smaller of this error will be, and the system will show the faster than before. So that target is we can increase the gain to 8. And let's see this time. And after we change from 6 to 8, this output, this amplitude will be increased. Let me change from 45 to 30 again. And the current PID output, this behavior is an ideal performance. It's not doing like a oscillation here. Because if the output control signal is oscillation there, it's not too good for the actuator. Okay, so from this decrease this process, the system doesn't have any overshoot. That is really good. However, we can see this error is decreased really slow. So to decrease this error quicker than before, we can still increase this KP. Also, we can decrease this Tn continuously. So for example, if I decrease this Tn from 25 to 14, let's try. And in the meantime, let's change this Tn only. Okay, and this time let's set 45. And in the meantime, I can make this dark blue a little bit thin. So wait a second. So we can set this set point, the line into line width into 2. Make it wider and make this blue smaller. So make it the thing. Okay. That looks better. And when we select this line, it will highlight here. It shows this is the line we are selecting. Okay. For this transition time, we can see the error between the set point and the feedback that decreased faster than before. Generally speaking, the current gain equal to 8 and the integer that is 14. That's basically good for this system. But we can see still it has an error there. But currently I will leave this error here and leave this group parameters here. And we will prepare to start to tune the derivative. And if we have an error here, once I enable this derivative, increase the value on the derivative, we will see the difference on this error. So now I will increase this derivative. Firstly, I will increase to 1 second. We will start from the small value. And the set point, let's set to 30 and watch this process change. So comparing with these 2 times, when the system running here, we didn't use the derivative. And now we are using the derivative at 1 second. And the PID amplitude change is much higher than before. Because with using this derivative, that makes this PID behavior become much proactive than before. The system reached its stable status. Let's change to 45. And let's see this rising time change. And from here, I can temporarily pause it and let's compare. So when the system runs here, we can compare. So it basically uses two grids to reach this set point. And after we use this derivative, so we can see the system reach to this set point actually faster than before, because system become more active than before with using this derivative. Alright, this is the basic procedure to tune the PID parameters for your system and for your PID controller. Basically, firstly, using the step response, we need to figure out what the gain of our process object and use this again to calculate the initial value of the PID gain only, and then use this again as an initial value, increase the gain a little bit, and try the system behavior. You will see when you increase the gain, the error between the set point and the process feedback, they will decrease. However, this gain cannot be a too huge value because the bigger gain that will cause the PID control more sensitive to the noise. So that will cause the issue for your actuator. To decrease the error between the set point and the feedback, usually we will involve the integration, the integral effects. Increase the integral effects, we will decrease the Tn, decrease the integral parameter. The stronger integration, the smaller or faster our error will be eliminated. However, if the integration is too strong, your system will show the overshoot. If your system has an overshoot, basically we could increase the gain or involve the derivative. The derivative can make the system response more faster than before. So if your system shows overshoot, you could try to increase the gain or try to increase the derivative value to solve the overshoot problem. But if your process has a strong noise inside, a stronger derivative will cause the PID control very sensitive to the noise. So in this video, I will basically mainly show this PID tuning procedure. And in next video, I will specially show when we increase the gain or decrease gain, increase the derivative or decrease derivative, what the behavior of your system response and the PID control behavior. In next video, I will use this group of reference parameter and increase or decrease for each PID 3 parameters and see how they contribute for the system response, how they will cause the PID control behavior. And see you in next video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.